We can both stand next to each other.
Good morning, everyone. It's a pleasure to see you all here in numbers after that phenomenal dinner last night. My name is Richard Stern. I'm here from Carnegie Mellon University in Pittsburgh. And it was a real thrill to be here for the INTERSPEECH in Jeju Island in 2004. And it's wonderful to be back here again in 2022, right here in Incheon. More than anything, however, it's my real pleasure to introduce Professor Daniel Lee, who is splits his time between being a Tisch University professor at Cornell Tech University in New York City, and also executive vice president, I believe, for Samsung, not too far from here. How he manages to split his time between New York City and here is remarkable to me. It was enough for me to come here even once, let alone go back and forth. As you all know from your notes, I won't repeat everything here, that Daniel was an undergraduate at Harvard University, followed by doctoral studies in physics at MIT after that. He then went to Bell Labs and a number of other places, including University of Pennsylvania and various other places, in evolving slowly from physics to neuroscience to the applications of computational technology to biologically motivated systems today. One of the most important challenges that we have is, in the light of the huge success that technologies based on deep learning have given us, we still have a hard time understanding what the DNNs are actually doing. And much of Daniel's research is an investigation to try to understand the underlying relationships between how DNNs solve problems, how they relate to biological systems, a number of very, very fascinating topics. It's a real pleasure here to have Daniel Lee talk about the application of neural networks to the practical problems that we're working on. And his talk will be followed by a discussion moderated by Haiga Zhang and Pedro Moreno from Google Research. So without further ado, please welcome Professor Daniel Lee.
Thank you. Thanks, Richard. We were just discussing, as old faculty, how when you teach signal processing these days, trying to motivate students with examples from music and speech is difficult because, these days no one knows what a CD is or what a tape recorder was or what, but now I think people know what phonographs are because they're coming back in vogue. So it just says, the more you wait, things come around in terms of things from the past becoming, fashionable again. So today, what I want to talk about is, how we can think about new representations, how we can kind of analyze these representations, especially in the context of multimodal learning, right? How do we process new types of data? How do we kind of correlate the features among these different views of the world? And how we can think about how we can quantify how well these representations will work, say, from an artificial intelligence or machine learning perspective. So in terms of what I want to do in terms of organizing my talk this morning, I want to start with, kind of some of my work in understanding the physical world from a robotic perspective, right? How do we make artificial agents that can perceive, can plan, can kind of make decisions, and be able to control their actions in a physical world, and how we can think about new algorithms, ways of doing machine learning that can kind of enable these physical devices. And then I'll introduce the idea of what I mean by manifolds, especially in the perceptual manifold context, what the manifold hypothesis is, and then talk about how they're represented in neural networks today. And then I'll try to explain from a kind of more academic point of view what we can do in terms of analyzing how well a representation works. What is kind of the way we can think about, from a machine learning perspective, whether the geometry of a representation is good or bad, and then try to use that as motivation to try to think about new practical applications of these deep neural networks for multimodal products and services. And I'll end then with some of the kind of current themes of research and what we're trying to do at Samsung Research at the end. Okay? So let's get started. Okay, so the kind of my main interest is, in terms of artificial intelligence, is really things that will touch the physical world, right? How do we take in information about the physical world from sensors? How do we then make decisions? How do we do planning? And then how do we actually change the world around us, hopefully in a better way? So in kind of a nice summary of this is my friend and colleague Sebastian Sung, who's the head of Samsung Research. He says that the motto should be, use bits to move atoms, right? What we're trying to do is use digital technologies and use the scaling that we're getting from faster computers, more memory, more data, but instead of just using that as an ends to themselves, think about how we can use that scaling to actually enhance our physical world around us and make our lives easier and better. So, this is one of the reasons why I joined Samsung, was the opportunity to really look at how we can take AI, machine learning technologies and apply them in a practical way across many, many different devices in the home, in the office, while you're commuting, thinking about ways that AI, machine learning can impact the ways you interact with mobile devices, with entertainment devices, television sets, screens in the home, as well as physical devices that are, say, mobile in the house itself, or things that are doing your work for you, home appliances. Right? So these are all the types of devices that Samsung makes, and what we're trying to think about is how we can leverage the growth and the advances in artificial intelligence to kind of give you a better experience, user experience across these devices. So that's really my ultimate goal in thinking about some of these technologies and how we can get to this kind of future as soon as possible. Okay. So as an example, this is some work that my colleagues have worked on in terms of learning complex robot trajectories. And this is, kind of a motivating example in terms of trying to take a simple robotic device. This is a robot arm with a hook on it, and try to have it learn how to pick up, say, your shoes. Okay? So this is an example showing you, think about the variability that we have in the different types of shoes, the different ways that you would have to use a hook to pick these up, and to be able to then place them, say, across a room or something like that. So here's an example showing you the different trajectories, right? And you can see that with the variability of different shoes, there are different types of motions that you need to generate, and you have to then reason about how, well a shoe would get picked up using a hook. Now in Korea, this is useful because, when we enter a house, we usually take off our shoes, and usually there's some, an instrument, or there's a person who always is managing your shoes for you. So think about, how we could automate this process, especially when you're, have your dirty shoes on the floor. So this is the idea, and the question is, how can we learn this using machine learning and artificial intelligence techniques? Okay? So the way we did this, and this was a project, we called this Pixels to Plans, Learning Non-Prehensile Manipulation by Imitating a Planner. These are some of my colleagues that were at the Samsung AI Center in New York, and we did this project a few years ago. And you see the authors of this paper. And the idea is, instead of doing traditional robotic methods, where you have some sort of perception module, which then outputs the pose of the object, and you have some grasp planner, and then you have some trajectory planner, and then you have some controller, all these kind of put together in modules. We wanted to see if we could kind of combine some of these things, especially the perception and planning modules, as an end-to-end neural network. Okay? And the way we did this was basically the architecture was to think about this in a kind of a self-supervised way, right? The conventional way of learning a machine learning algorithm like this, or a neural network, would be to do supervised learning. What that means is that, let's say that you have a view of the shoe from a camera, a depth camera, and you want to then generate a motion trajectory for an arm. Now, the kind of conventional way would be that you would take a whole bunch of examples, input-output examples of the view of a shoe, and then you would then have, the motor commands that are going to the robot arm that would be needed to pick up that shoe. You would collect, lots and lots of examples of this, and hopefully train a neural network that would learn to input map from, the sensory input to the motion trajectory itself. Now, this is a very difficult process to do because you don't have a lot of training examples. And so the idea would be to try to leverage more self-supervised techniques to learn this task. And so the way we did this was we had a teacher system here, which was using more conventional robotic techniques to generate this plan. So the way you would do this in conventional robotics is you would take not just a single view of the shoe, but you would take multiple views of the shoe. You would build up some sort of 3D point cloud model of the shoe. Then from this point cloud model, you might think about some sort of wireframe structure. You would then try to do some grasp planning in terms of where the hook should go into the shoe. And then once you have kind of the location of where the hook should go, you then feed that into a path planner system, right? So typically you would use something like an RRT, a rapidly exploring random tree planner system, which would then compute all the different possible trajectories and try to score the best trajectory to use to pick up the shoe. And then you would output that plan, and then you would then generate, the corresponding motor torques to execute that plan using inverse kinematics. Okay, so that's the conventional way of doing this. And so what we wanted to do is take the conventional robotics approach, use that as for self-supervision, use as a teacher, so that a neural network that has less information as input, so instead of having multiple views of the shoe or having any sort of notion of 3D point clouds, just takes a single view of the shoe and is able to imitate essentially this teacher system that outputs the path plan directly. And so by doing this, we can then basically take multiple examples, we can do data augmentation, we can then have the teacher system train this neural network, which then can generalize from a single view of the shoe to kind of a corresponding motion trajectory that the robot arm can use to pick up the shoe. So this is the way we can do this. We leverage, these kinds of self-supervised techniques. We then can train this, pre-train this, and then you can then fine-tune this again on new shoes if you need to for the future. Okay? So that's the kind of system that motivates my example in terms of thinking about how we can leverage machine learning techniques using not so much training data, thinking about self-supervision, representations of the learning process that will then allow us to do this kind of task. Okay? So for the future now, what we would love to be able to do is take, say a simple robotic system like this, and to make the kind of human-robot interface much more complex. Right? So we're talking about now of using new voice technologies that will control home robotics in the future. Right now, if you think about how we interact with these robotic systems, they're very, very scripted and very, very naive in terms of the way you interact with them. And so, what we would like to do is use some of the new exciting technologies that we're seeing here at INTERSPEECH to try to interface better with, say, these new types of mobile robots that can do better navigation or manipulation or being able to do this kind of interactions with the physical world and to be able to control and direct these systems using speech or language commands, right? So that's what we love to be able to get to. But how are we going to do that? How are we going to combine all these types of different types of modalities to generate these types of intelligent responses? And this is where I think we need to think carefully about what we mean by these different modalities, what their representation should be, as well as the types of data that we use to train these systems, right? So if you wanted to really build this kind of intelligent home robot system, you want to use vision, right? So you want to be able to use the multiple cameras that you have. You want to be able to use speech. You want to be able to audio signals from the environment. You also want to be able to use language, text representations, and you want to be able to generate things like complex motion trajectories. Right? So this are the types of data that you want to use. And you think about, these different modalities, they have different types of noise properties. They have, the different structure in it. And so you have to think carefully about how you're going to combine these things to be able to generate, make a system really intelligent. Now, these days, the approach to this problem would be just to throw it into a big end-to-end machine learning system, right? You take all your input modalities, put them into your inputs, try to generate your outputs for your actuators directly, and then train on, millions and millions of examples of this. And hopefully, you'll be able to succeed in correlating all the different modalities with each other, being able to align the representations using this kind of tabula rasa point of view, and to build a system that truly can generalize across the different modalities and be able to generate intelligent responses. Now, this is an extremely challenging way of doing this problem, but this is what people are trying to do right now at a number of places. They're collecting these types of data sets, they're putting it all together and trying to build these end-to-end systems. Now, I'm a little skeptical that this will work, even with trying to scale things up, especially with physical world robot data, because it's so difficult to collect that kind of training sets. It's very difficult to generalize enough examples to be able to do this kind of alignment of all the representations and being able to generalize to new domains in this fashion. And this is what you're seeing is kind of, as another example, AI for autonomous driving. Right? There, we're trying to see these examples where you're just trying to collect all the different inputs that you could get from an autonomous car and trying to learn in some very simple supervised fashion what to do in these different situations. And you see that the number of corner cases in the real world is just enormous. And so even though we're trying to collect all this data and all these training examples, there still is a problem of being able to, validate these systems and being able to do this in kind of a large enough, fraction of times that you'll make it safe. So this is the problem. So what's the solution to this? Rather than just trying to, do a brute force technique to this learning, can we think about more intelligent ways from a design perspective, using structure in the problem to help us achieve this task? So this is a real fundamental issue, and this is why it's hard to collect enough data, right? Is the variability that we see in data is enormous. And we, in the speech community, recognized this many, many years ago, right? That dynamic time warping was an important aspect of variability in speech. And if you think about kind of the variability that you generate from dynamic time warping, it's, a very large set of signals that correspond to the same underlying, say, word, right, or text, right? So this is really important. We have to understand that variability in kind of these kinds of physical types of parameters, underlying parameters of the signal, causes this type of variability in the data set. For vision, right, pose and lighting invariances is very important. And of course, we have effects from occlusions and background. These are the things that really require us to understand the structure of the data in the domain itself. Now, the typical way we do this in machine learning these days is just to collect as much data as possible, but you can see that these sources of variability are infinite. So even if you collected 1 billion examples, you still will have holes in terms of this kind of invariance properties or the equivariance properties of the data that you want. So how can we, think about a more a principled way of approaching this variability problem? And so this is some work in the last few years that I've been working on from a more theoretical academic point of view. And this is to understand what we call the manifold geometry for perception. And this is work with Chaim Sampolinsky, who's a professor at Hebrew University in Jerusalem, and Harvard University, Suyong Jung, who just became a faculty at NYU, and Uri Cohen, who's finishing up at Hebrew University. And these are some of the papers that we've written. And the basic idea is to go back to kind of old-style machine learning and think about what it means for a neuron to classify something, right? So the very simplest kind of McCulloch-Pitts model of a neuron is this basically almost the same as what we're using today, except the nonlinearity instead of, say, binary is a ReLU type of nonlinearity. But you have some set of inputs into the neuron. You have some synaptic weights. You do some linear summation, and then you have some sort of output nonlinearity, right? And so if you think about this from a geometrical point of view, what a neuron does is takes the vector space of inputs and tries to classify that, if you think about a binary output, in terms of some sort of separating hyperplane from one side where the inputs do not activate the neuron to the other side of the hyperplane where the neuron is activated. This is the very simplest picture of a neuron. And what neural networks do is just basically cascade many of these things together. And at the final output layer, you will have some sort of output neuron that looks like this to say, let's say, make a binary decision. Okay, so that's the basic structure of a neuron. And now, what do we know theoretically about what this neuron can do? And this goes back to Tom Cover, and he was able to characterize mathematically how many different dichotomies a single neuron can make if you give it p training of examples in an n-dimensional space. So given p points in n dimensions, how many different binary labelings of these points can a neuron correctly separate? And he was able to come up with this mathematical formula. It's a combinatorial formula. And this is true for any set of p points in n dimensions as long as they're in what's known as general position. Okay? And so this is the formula. And it's always less than equal to 2 to the p, because 2 to the p is the number of binary labelings you can totally have. And you can then derive this formula very simply. It's a simple recursion relationship that you can basically do by mathematical induction. Okay? So this is really kind of the underlying understanding of what the capacity of a neuron can do, like how many different binary labelings a single neuron can basically separate. And if you look at this, if I plot kind of here the number of binary labelings a neuron can separate versus the total number of binary labelings, that's that fraction on the vertical axis, and we look at this as a function of the ratio of number of points over the number of dimensions, I call this alpha, what you see is an interesting property, right? As long as the number of points is less than n, any neuron can always basically classify your data set. This is something known in machine learning as the VC dimension, the Vaptis-Chervonenkis dimension, and that's true in general. But we see that as we increase the dimensions, so if you start with n equal 3, as you increase the number of training points, then slowly the neuron is unable to basically, for a random labeling, it's not going to be able to classify it correctly. And so it drops, the performance of this drops. But if you go to higher and higher dimensions, as you go to n large, you get to something where basically if p is less than twice the dimension, the neuron can always classify the training examples. And when p is slightly larger than twice the dimensions, then the neuron can never classify the examples. Okay? So this is something known as a phase transition in physics, and this only occurs in kind of the big data limit, where the number of dimensions and the number of training examples gets larger and larger. And so this critical kind of factor, number of 2, is what characterizes the capacity of a single neuron in a neural network. Okay? But we want to generalize this because we want to think about robustness. The way we think about robustness in machine learning is we think about margin. So instead of just correctly classifying the points, we want to make sure that there is some sort of boundary distance between the points that are correctly classified, so that if you perturb these points a little bit, you will not basically change the classification. So that's the notion of margin. And so this is the idea of maximizing margin in machine learning, is to give you the maximum robustness for a neural network. Now, how do we do this from a statistical point of view? Well, there is a theory by Elizabeth Gardner back in the 80s who showed how to calculate the capacity of a neuron to classify a set of p points in n dimensions with a finite margin. Right? Before, the calculation Tom Cover did was 0 margin. Now she's generalized this to finite margin from a statistical point of view. And so the way she did this calculation, I won't go into the details, but it's something known in statistical physics as a replica trick. And the idea is you have to kind of calculate in expectation the volume of the set of solutions with this margin problem. Now, you want to calculate actually the expected value, the log of the volume of solutions, because that's the intrinsic kind of scaling that you need to have. So how do you calculate something, the expected value of a log of something? Well, the way you do this is you write the log as a limit of powers. And then you calculate actually the expected value of powers, and then you take the analytic continuation where n, the power goes to 0. And that's how you calculate the expected value of a log. And that's basically the fundamental calculation that she did. Okay? Now, if you do this, you can actually get the capacity of a neuron in terms of the different margins you want. So what you see here is on the left here, you see that as you increase the margin kappa, you see that the capacity goes down. That is, the number of points that you can basically classify with that finite margin will drop, and that ratio p over n then falls accordingly. And you can also do a theoretical calculation of which points will be actually on the margin. These are known as the support vectors when you think about support vector machines. So how many of these points will become support vectors? How many points will become interior? You can calculate this directly from the theory, from the statistical point of view. So this is kind of a nice theory of understanding what a neuron can do with robustness in terms of classifying a set of points. All right? But as I told you, when we talk about real data sets, we're not talking about points anymore. We're talking about infinite variability, where you have, as you change some physical parameters, such as time warping, or you change the pose of something, you're going to generate in your data set an infinite set of inputs. And these we would call perceptual manifolds. And these typically have lower dimensions because the number of degrees of freedom of the variability is smaller than the underlying embedding dimensionality. And so we have these low-dimensional manifolds that represent, say, an object or a word or some sort of identity, like a dog here. Right? And so instead of having points now, we have to think about machine learning with manifolds, with infinite sets. So how do we do it? So the way we have to characterize this type of problem is we have to generalize this theory that I just told you about. So what we do is think about how we classify sets of manifolds rather than sets of points in machine learning. We then have to define the geometry. So we have to have some way of deriving the notion of how geometry influences the capacity of a neuron. So this is how we define the problem. We have these kind of infinite sets now that are basically characterized in terms of the geometry. And then you can actually then, with this calculation using the replica trick, you can actually calculate the capacity of a neuron in terms of being able to classify a set of manifolds rather than a set of points. And what you can then do is you can then, you generalize the notion of support vectors to manifolds. You can have different manifolds that are touching the support planes. You can have different manifolds that are interior and different manifolds that are embedded in the support planes. And you can calculate all this analytically, and this is what the theory shows you how to do. I won't go into the details here, but this is kind of the idea. All right? And so what you can then see is that different geometrical properties give rise to better or worse classification performance in a neural network. So what you can see is that, if I vary the radius of the manifold, the effective radius of the manifold, how does that affect the performance of a neuron to classify these set of manifolds? Or if I change the effective kind of embedding dimensionality, that is the kind of intrinsic dimensionality of the manifold, if I change the dimension, how does that change the performance of a neural network? And so you have this trade-off between basically trying to shrink the size by the radius or by changing the effective dimensionality of a manifold in terms of trying to improve the performance of a neural network. And you can see then that we can actually characterize the performance of a neural network in terms of these two quantities, effective radius and effective dimensionality of the manifold in terms of how well the neural network can handle this type of data. Okay? So now what we can do is we can actually use the statistical properties to kind of understand how representations change in a deep neural network, right? So what you have is you have some geometry of your input representation coming in at the input layer. And what does a neural network do? Well, at each layer, it's just going to transform the geometry of these manifolds so that you go from some radius and dimensionality at the input layer to the next layer, you're going to change the radius and dimensionality. And then the next layer, you change the radius and dimensionality of all these perceptual manifolds until at the final layer, you will have some output neurons that can successfully classify all the different classes in your data set. And this is exactly what happens in your brain as well, right? If you look at kind of how visual or acoustic processing works, right? You have basically a deep neural network where you have some input representation, and that gets transformed layer by layer in the brain to these different representations until finally at kind of the output layer of your brain network, say, at inferior temporal cortex for vision, or, in acoustic auditory cortex, right? These are the different representations that you can actually read out identities and objects and those types of properties that you're interested in without the underlying perceptual variability that you have at the input layer. So the idea is then to analyze deep neural networks using these tools. And so, we can do experiments where you take different types of input manifolds. You can do this with kind of data augmentation techniques in machine learning. You can generate, warped manifolds. You can look at big data sets like ImageNet and just look at the set of all dogs as a manifold, as a big point cloud manifold. You then put these into a neural network, and you can then measure how different deep neural networks can basically change the geometrical properties of these manifolds as the data progresses through the different layers. And this is something that we've analyzed, and you can then see the effect of learning or the effect of different learning algorithms in terms of how these manifolds are basically reformatted and transformed through a deep neural network. Okay? Now, and you can measure different quantities, geometrical measures, and you can then try to correlate the performance of a neural network in terms of generalization performance with how well the geometry is changing. Okay? And this has been recently extended. This is a work by Josh McDermott's lab at MIT in terms of thinking about using these techniques to understand invariant speech recognition. So here again, you have variability in the speech signal itself. You want to be able to, say, classify different words. And now you're looking at how the manifold geometry changes as you go through, say, a convolutional neural network, or in their case, they also analyze the deep speech 2 neural network in terms of using more recurrent types of units, gated recurrent units, and thinking about how those different layers are changing the format of the speech manifolds as it progresses through the neural network. Okay? So these are the types of things that we can do from a theoretical perspective in trying to ground a little bit better, how these deep neural networks are working in actual use. All right? Okay, so that's what I wanted to say from a theoretical perspective. Now I want to shift gears a little bit and try to say, well, look, these are all exciting new results. What are we trying to do from a more practical point of view? At Samsung Research, we're fortunate to have a large language and voice team. I'm very pleased to have as colleagues Chan-Woo Kim, who's the head of the language and voice team at Samsung Research, and also Hoon-Young Jo, who just joined us to help with on the text-to-speech part and some of this acoustic signal processing parts of the team. And so what we have at Samsung Research, I think like a lot of companies that are interested in voice and speech and language technologies, we have a number of projects, related to the latest machine learning techniques and AI techniques for, automatic speech recognition, for processing more generic types of audio, as well as, generating speech from text-to-speech, as well as understanding language models and being able to correlate that with the underlying speech signals themselves. So these are the different areas that we're working on. Here is some of the, I'm happy that a lot of our colleagues have presented already here at INTERSPEECH. We have a number of papers that we've been involved with. So, different aspects of trying to make these systems work in the real world. So, being able to use better vocoders for things that could be on device versus in the cloud for, speech recognition. We could have different ways of doing speech translation, so cross-modal techniques, being able to use text representations as well as speech signal representations and correlating those together to give better performance for translation. That's another paper here. And then how we can use, basically use non-parallel corpuses and use that to still improve the performance of voice separation or kind of signal, acoustic source separation, right? So these are the types of projects that we're involved with. I don't know all the details, but if you have a chance, hopefully you have a chance. Sometimes you can speak with our authors coming from Samsung. Okay. And so this is the ideas that we're looking at, right? Different new models. There's so much happening with convolutional neural networks in conjunction with transformer models, with conformers, putting that all together, whether you want different passes through your signal set. How do you make it so you have low latency? How do you make it so that they're more efficient in terms of on-device performance? How do you make it so that you can have better training, all right? So more few-shot learning types of applications. How do you personalize these systems to individual speakers? How do you use better context in these devices? Using, again, multimodal representations coming from, say, cameras or other types of data. The more structured data that might come in. How do you integrate that into say, a voice type of assistance? How do we then make sure that we cover all the different types of speech in the world, right, across different languages? When you have low resource languages, how do you deal with that? These are all the types of things that we still need to improve in terms of making better models and architectures and training techniques that we can actually deploy so that these things will actually work when you put them on real devices. So these are the types of things that I'm excited about. And I think here at INTERSPEECH, a number of you have been thinking about these same problems and how we can try to really build systems that could really make an impact in the future. So that's all I wanted to say this morning. So just to summarize, I hope you are thinking as you do your work in terms of better representations and learning. How do we think about the actual structure and the data itself, especially in the speech and language domains? What is that structure that we want to exploit when we do our training? One way of thinking about this structure is hopefully through geometrical measures that I've introduced here, how we integrate mathematical intuition about these signals itself into our systems, and how we can actually then understand our deep neural networks better, right? Can we use and generate some of these analytical tools so that when we do things like model architecture search or hyperparameter tuning, that instead of just running these things naively, brute force, just trying all possibilities, that we can use the structure of the representations and the data itself to help guide building these systems. And finally, I hope that a number of you will be able to build some of these new exciting applications that we're going to see in the future for real-world devices and services. So thank you very much for your attention, and I'd love to have some more discussion about that later. All right, thanks. chairs too, yeah.
Thank you very much for the excellent talk. We're going to have a brief panel discussion. I'd like to invite to the stage Heike Zen and Pedro Moreno from Google Research. You're here somewhere.
Come in here.
Oh, there's Pedro.
Hi guys, come in here. Yeah, come on. Okay.
You sit in.
I think you're sitting here. And I'll
I remember that.
Yeah, I think there'll be one more chair here. Hi, how's it going? Hi. Hi, Pedro. Hi. Yeah, great.
We're going to begin by comments from the two panelists on the talk, and then some general discussion. Which one of you would like to go first?
Maybe you can briefly introduce yourself so everyone knows who you are, and then
Yes.
give some comments.
Hi, good morning. My name is Pedro Moreno. I'm a senior research director at Google, working in speech recognition, contextual modeling.
Hi, my name is Heike Zen. I'm a research scientist at the Google Brain team in Tokyo. I'm mainly working on speech synthesis.
Okay, we'll begin by some brief comments by Heike and Pedro on your impressions, what we just heard.
I think it was a very interesting presentation, and this is something I often wonder. We are building these massive neural networks, and I often think, especially in industry, we are engaged in this game of my network is bigger than yours, and of course we see improvements, but I think we are failing to really understand what is going on. And I personally hope, as an industry and as a community, we switch our thinking from bigger, more data, into really trying to understand what is going on. I think in the past, for example, in the area of speech recognition or even TTS, we had the concept of different knowledge sources of knowledge, lexicons, grammars. We had some ways to inject human knowledge, but all that has disappeared. And of course, there are reasons for it. Performance is better. But there are, as the speaker mentioned, there are corner cases. And you remember the first keynote on Monday, these corner cases are starting to be dangerous. So I like your presentation, and I think this is something we need to do. But at some level, I think we are lost.
Okay, so let me talk about what I found from the presentation. So I'm mainly working on the speech synthesis. So that unlike speech recognition, so the speech synthesis is a one-to-many mapping problems. So I think in your presentation, you talked about, say, the infinite dimension the observation to the manifold. So in the speech synthesis case, we actually need to, for the, say, the generation task, we need to generate these, say, the small manifolds to the infinite dimension. Then the tricky part is, say, that sometimes it is appropriate, sometimes some point of the, say, the manifold is appropriate, but some points of the manifold is not appropriate based on the contextual information. So I really would like to see how we can, say, or combine the multiple modalities so that these, say, different modalities can actually, say, reduce the ambiguity in the to generate the sample. So I hope that, say, based on this kind of, say, the research work, I hope that we can find a way to model multiple modalities into the single representation, then use that information to generate a sample which is appropriate from the many different perspectives of the modalities.
Daniel?
Yeah, no, I totally agree. I think, coming from an industry perspective, where, as Pedro and Heike mentioned, that we're driven by performance metrics, right? So, word error recognition rate for speech recognition, or, perceptual kind of measures for how good the speech sounds. And in terms of improving that performance, we've lost sight in some sense of trying to understand what we're building a little bit, as well as trying to incorporate other sources. We used to be able to incorporate sources of knowledge such as in speech generation, what formants mean, right? I mean, we threw this all away now with machine learning systems, or sources of variability that we know happen in speech. We just now train using huge amounts of data. So I'd love to be able to see if we can kind of do a little bit more principled approaches that combine some prior knowledge that we have about actually these domains, whether it's speech generation or speech recognition, and put that together with these more machine data-driven systems that will then hopefully allow lots of more innovation and progress in these areas. But we don't know how to do that yet. And this is where I think academics or students out there, these are exciting times for you to think about what the next generation of these systems will look like.
Well, I've sort of come from a tradition where it was important to try to know what was going on, to listen to the speech, to look at the waveforms, to look at the displays. And every time we try to build knowledge into the system and then do a controlled experiment, the blind classification methods, it's maddening, keep working better, putting people like me out of business. Do any of the three of you have any thoughts about how to more effectively put knowledge back into deeper learning?
Can I comment about that? So recently in the speech synthesis, so obviously after the neural vocoder comes, so that people tend to put okay, so let's say leave the neural network to learn the direct mapping from the acoustic feature to the waveform. However, recently people started to say reviving the signal processing knowledge. So that based on, so many signal processing techniques are actually differentiable. So that you can say integrate the differentiable the signal processing into the part of the neural network, then we can actually interpret what's going on in the domain. So I think that, of course, I think that the traditional signal processing based the audio generation approach may not be able to achieve as their highest quality. However, so that by integrating the previous knowledge to the model, we are actually seeing that the model can achieve the very high quality. However, it still provides the interpretable representation as well as the controllability. So I think that, at least in my domain, so that I'm seeing that the signal processing knowledge is getting more important to achieve the controllability as well as the quality.
So, Rich, you're asking about how to inject knowledge and structure. And I agree we don't have a clear picture yet. But I think there is some light at the end of the tunnel. I see some initial ideas, for example, in language models where n-grams and handcrafted grammars, which, for example, think of numerics, right? Numerical systems in many languages have a very clear structure. And if you do nothing, if you just throw data at the system, you can run into weird situations. I'm thinking, take French, right, where you say 420. If you are not very careful and people say 420, which should be written like 80, the recognizer might actually give you something wrong, right? So I think there are initial ideas where people are starting to figure out how to inject knowledge through memory structures or systems that are teacher-student systems that are kind of guiding the neural network to ignore these spurious correlations. But it's early days. And I think you're right. We see really how the neural network is able to learn anything. I can think of an example where for multilingual speech recognizers, some folks in Google and probably outside there, they train the network to produce UTF bytes. And you think about it, this is insane because the neural network is not only learning how to map from acoustics to internal representations, but it's also learning how UTF bytes map into characters, which is, UTF bytes is rule-based, and the network is learning that. So.
Yeah. No, I mean, it's difficult, as you mentioned, to inject structure in it because these days, you have these almost trillion parameter large-scale models that you just throw the data at, and it seems to generalize very well. It handles all sorts of inputs, and they beat kind of a lot of ones that you try to handcraft. Now, maybe one way is, as Heges was saying, you do some inductive bias to initialize the system so that it can be more efficient at learning with some of the models that we know about. But then still try to be able to leverage, being able to use large data sets to try to tune these things. So that's the issue. Is that kind of, you don't want to be constrained by any prior biases that you might have about models, but you also want it to be flexible so they can kind of accommodate all this huge amounts of data, right? So putting those two together is challenging, and to do it in a way that is efficient and is going to scale and allows us to build new sources of knowledge into these systems is difficult.
Thank you. Shifting gears for a moment, one of the things that I found the most fascinating about your talk was the discussion about all these investigations into fundamental limits of the power of neural network-based structures. This is a literature that I've been totally unaware of up until now. I'm wondering how you see knowledge of and appreciation for these boundaries guiding the direction of practical systems.
No, I definitely think having some scientific constraints in these systems is important, and to understand that. I think, for instance, I'll give you a good example, right? A signal processor, we all know about Nyquist theorem, right? And what the limitations of Nyquist mean in terms of what you can do with a certain set of samples, and what the ambiguities are. But these days, how many times I heard students come in and say, oh, I'll just train a neural network that overcomes Nyquist, right? I mean, again, it's a question of, you should understand that there are some physical limitations. You should understand where they come from. Maybe you don't know how to characterize all of them yet, because that's still theoretical. But we should have some understanding of what the limitations of these systems are, rather than just thinking that these are magical techniques that you should just throw enough data at it that they'll solve these problems, which is not going to happen, right? It's impossible.
Yeah, I think of the Shannon channel capacity theorem and its impact on communications and coding. Pedro, Hege, any thoughts?
I agree. It's useful, but I also have to say I'm constantly surprised. I can give you an example. We have been working in speech recognition and voice conversion for people with disabilities, people who had a throat cancer. So their voice is severely distorted. From a signal point of view, if you look at the problem, you would conclude it's impossible to do anything. But it's remarkable how even in situations where the voice is very, very distorted, you cannot hear, you cannot understand a thing, these neural networks are able to recover and synthesize voice that is reasonable. So there is this sense of wonder, despite the physics and theoretical limits. Perhaps they are looking at information, they're looking at long-term correlations, they are taking advantage of thousands of hours to extract knowledge, right, that things like Shannon might not consider, right? But there is this magic, so it's hard to deal with it.
But I might argue that what you're seeing there is that you're learning something about the structure of language rather than the structure of the speech signals, right? That there is a constraint on the language, that's what they're learning from, right?
Yeah, I can share my brief experience. I'm not sure whether it directly relates to this topic. So I used to work with the people in DeepMind, and these people didn't have much experience in speech. So sometimes having the knowledge in speech is very useful, but sometimes it constrains us to explore the ideas. And then my colleague, tried to explore, the completely autoregression model for the neural network-based audio generation. And I spoke to my the colleagues about that, and they said that they were that person was a signal processing expert, and he said that it was a completely insane idea, so it is better to stop exploring that direction. However, because these people didn't have much prior information about that, so that they just tried what they wanted to try, and it worked, and it was much better than the existing system. So I understand that, of course, it is better for us to have enough knowledge about, the domain. However, it is important for us not to be constrained by this the prior knowledge. I think that it is still better for us to have while learning their basic theory, but it is also better not to be constrained by this prior knowledge.
I remember an experience I had a few years ago before the beginning of the DARPA RATS program. This was a program to transcribe speech in very noisy data. And a bunch of us were invited down to Arlington, Virginia, to listen to the real data that they were interested in. And I'm listening to this audio in English in noise, and it's absolutely unintelligible. And I'm thinking to myself, well, I'm happy to take all that money from DARPA, but there's no way we're going to be able to solve this problem. And the fact is the program was successful. It met every milestone ahead of time. And my takeaway from all that was not to underestimate the power of the machines. And this was even before the advent of really deep learning. So I think there's a remarkable future in front of us where we can rely on automatic analysis and classification for all sorts of things that go beyond our own perceptual abilities. And wonder if you have any comments on that.
Well, I think, as you mentioned, I don't think human performance is not a fundamental limit, right? It's what the brain right now, in terms of our experience, has done. But physical fundamental limits are real scientific limits in terms of the underlying physics or whatever itself, and whether there is some structure and that's coming from higher levels. That's maybe what you learn with these neural networks, or being able to extract things because there are certain properties of the noise themselves that you're learning rather than they're just arbitrary noise. So these are all the things that I think we're discovering with neural networks, and I agree that we shouldn't be constrained. We should try these things if they work, but we shouldn't just say, hey, they magically work. We should also try to think about what it means when they work. Like what's happening there, rather than just, oh, I wrote my paper and then move on to the next topic. I think we should understand it.
Yeah, to be honest, so after the success of the autoregressive the neural waveform generation model, there was the flourish of the actual research to understand what is going on, and then we actually could find the relationship between the existing theory and what's going on in that model. So I definitely agree with you. So I think that, of course, so that this kind of disruption can come from the outsider. But so that once it happens, so that we can invest our time to understand what's going on. Then, after understanding the key concept of the model, so that we can apply our knowledge to further improve the quality of the new technology.
I agree with you, Rich. The future is very interesting for sure. We're going to see a lot of new things. I'm surprised. Every 2 weeks, you see some new amazing technology. And I often joke, it's hard to keep up, right? But I think we need to figure out ways to inject knowledge. As I said at the beginning, not only is not scalable to throw more data, I think it's also dangerous because we don't know what are the corner cases that the network is not learning. Okay, maybe in the speech recognition it's not really dangerous. Okay, the recognizer will produce something wrong, but in other applications it can be. So I personally think we need to do more extensive testing. Many times the demos are fantastic. I remember in the early days of Tacotron, everybody was amazed. We were doing reviews. And I remember there was an engineering review. I think, Hega, you were there, maybe. And the demos were fantastic. And I actually asked, is the network guaranteed to always synthesize the text? And it was a loaded question because I knew there was a small probability, and this is early days of Tacotron, that the network could go crazy. And this is because, we were very enthusiastic about the technology, and the team had to go back and figure out, okay, we need to make sure the network is not going to get into this instability. So this kind of safety checks, I think is an area where we will have to invest more time.
Okay, according to the big clock in the front that most of you can't see, we have about 7.5 minutes left, and we wanted to leave some time for questions from any of you for any of the three panelists, Daniel, Hega, and Pedro. So questions or comments from any? Yes, go ahead.
Maybe
Can you get a microphone to him?
Do we have an extra microphone?
ahead. We'll take one there. Go ahead. Stand up and ask the question.
Here comes the microphone. Great.
Hello. Nice talk and congratulations. I was wondering, with the popularization of deep learning, AI, artificial intelligence, has gotten less and less explainable. We've had like a diminishing reduction of techniques like decision trees, rule-based systems, and like you guys said, we are not like most people are not knowing what they are doing. So do you see those techniques like coming back and like the popularization of deep learning reducing?
I can give you my view. In particular, for example, the case of tree structures, I can tell you in production situations, they're still very useful, right? Because you can approximate the decisions of a neural network with a tree, and it's super fast. So I think there will always be a role for solid computer science. It's just that when you publish the paper, you might not think of a most efficient implementation. In terms of understanding what the network does, I think there is a bit of a debate, at least in companies like Google, whether if you're building a complicated system, for example, an assistant, right, where the input is a speech and the output is actions, whether you should build a modular system where there are intermediate entry points, speech recognition, NLP, actions, or you should build an end-to-end system. As you can imagine, building an end-to-end system is kind of sexy, but it reduces completely your ability to do fixes, to understand what's going on. So I personally think we should have more modularity. At least maybe each module is a little bit unclear what's happening inside, but you have intermediate entry points. And I also see solutions where maybe the modules that you are connecting do not fit necessarily of the final output, but they are able to read intermediate representations. So these are middle grounds.
So for example, in the text-to-speech synthesis, we are still heavily using a rule-based system as well as decision trees or HMMs or more interpretable models. The one example is the text normalization. So we have neural network-based text normalization. For example, you have, say, the numbers in 1,000, or then it converts to the series of phonemes or expanded format. So that if you make a mistake in text normalization, it completely changes the meaning of the sentence. So this is not acceptable. So for these cases, we are still heavily relying on the rule-based or more interpretable system because we need to make the point fix. And then if it makes it completely, so for example, if it completely changes the meaning of the sentence, it is totally unusable. So I think that we need to, so I think that both systems will reside. I think that we coexist. And then so in the future, we may be able to come up with the completely robust system, which is not interpretable. But at this moment, we are still heavily relying on these rule-based systems.
And I think what you see is in many commercial systems, you start with some sort of neural network core idea, but then when you go into production, you see, lots of hacks that happen that are more heuristic, and people are building these things to make sure that, strange things don't happen. So you actually see that in practice a lot still, even though we talk, theoretically that it's a big neural network.
We have time for just one more quick comment or question. John, go ahead.
So thank you very much for an outstanding panel and also the talks from this week. Over the last 5 to 7 years, the number of students that we have now as ISCA members has doubled. And so I'd like to ask, you're the leaders of industry. one of the challenges in the academic world is that the resources that you might have versus what the academics have are significantly different. So I'd like to ask, to address the students that we have here and online, what advice do you have for our PhD students and master's students that are close to finishing? What can they do to better prepare themselves to maybe go into a job market and hopefully get hired by your companies?
You guys want to start with Google?
I would say what I think academia should not waste time is trying to compete necessarily on this race to do bigger and better, I mean, more data, systems that require more and more TPUs. That I don't think is useful. I think addressing the limitations we were discussing, understanding what is going on is super important. Areas like injecting knowledge. I personally, when I come and see the papers, I don't necessarily care about, oh wow, is this a new state of the art? What I care is to see that the student is thinking and analyzing a problem. Maybe the results are not amazing, but they are understanding. This is what I think we look for. People that can think on their feet and understand the problems. Yeah.
Yeah, I have the same impression. I think that we are looking for the people who can understand the problem and then say or come up with their idea how to tackle the problem. I think that they say learning the process is more important than say keep beating say the state-of-the-art system. So I hope that the PhD students to learn say, for a given problem, so they understand the problem and then to figure out how to tackle the problem.
Yeah, and I agree with you that industry can win on scale, but in some sense, ideas there are more incremental. So I think academics, I mean, we would love to see more innovative ideas and understanding and new ways of approaching a problem, you know, even if it's not at scale or with the top performance on the benchmarks, right? That's where I think academics should focus.
Okay, well, thank you. Please let us thank our keynote speaker, Daniel Lee from Cornell Tech and Samsung, and our two industrial panelists, Ega Zhen and Pedro Moreno from Google. Thank you for a very fascinating discussion, interesting commentary. It's a pleasure to be here.
Thanks, Richard. Great. Thanks, guys.
Just maybe a station identification type of an announcement. Just want to let you know that we're going to have closing ceremony at 4 p.m. this